I know lots of other classes have exams too around this time, so apologies for that. This one's small. Hopefully you didn't spend so much time stressing out over this. Okay, so nice. So a medium-sized class for today. So you'll remember the basic idea with the general linear model. We walked through this huge arc over the course of part 3 and the beginning of part 4 so far. We started with this idea that we have observations of random variables. Random variables are generally unknown to us, but what we see are these realizations of some underlying random variable. And often we have questions about the parameters of the underlying random variable, like the mean. So we talked about the central limit theorem, which allowed us to make claims about the distribution of sample means without ever having to see the underlying distribution itself. And this was such a powerful result, we started building on statistical tests on top of the t-distribution that's given to us through this construction we did using the central limit theorem. And this was incredibly powerful. We performed single sample t-tests and 2 sample t-tests, testing for whether the mean is a particular value and whether 2 means are equal. And so what we did in part 4 was extend this idea of the t-test into a more general environment. So with the t-test, we can perform particular types of statistical tests, but sometimes we want something a little bit more powerful. And it turns out this idea of regression, where we not only have a line representing the mean, but also a line representing the slope, this lends itself very nicely to the types of tests that we've been doing with t-tests, right? Regression is essentially a very flexible t-test. And the approach we took was simply to draw a line like this. So we have our linear model. We're just simply drawing a line. We have our y variable. We have our intercept coefficient. We have our slope coefficient. We have our x variable. And then we have some error term. And this error term was just essentially how wrong the model is for each individual data point. And we talked about how we interpret each one of these coefficients. We talked about beta 0 being the intercept, which when there's no slope, this gives us the mean. So when we don't include a slope, beta 0 is just interpreted as the mean, which is the same idea as a single sample t-test. When we do have a slope, we interpret beta 1 as that slope. And the way we say this in English is that we have a beta 1 change in y for every unit change in x. So we increase x by 1, y changes by beta 1. So we're just increasing by the slope of the line. And what that also means is when we have a slope, then beta 0 is interpreted as the model estimate at an x of 0. So it's at the vertical intercept. And then epsilon is just the error term. So it's like how wrong the model is at every given data point. And then the thing with OLS estimation is ordinary least squares is we're just trying to minimize this this term here. This is all of the squared error terms. So we take each error term, we square it, we sum it all up, and then we try to pick parameters that make this thing as small as possible. And I like to just note here, we're not going to do this minimization procedure, but if you like calculus, you like math, and you like optimization problems, this is an optimization problem. We're just performing a minimization. So we take the first derivative of this model, set it equal to 0, and then we just solve for the parameters beta 0 and beta 1 that make this this error term as small as possible. So we have an objective function, minimization approach, and then we can recover beta 0 and beta 1. And this is something you can do. A lot of you are very skilled at optimization problems, and this is not outside of the scope of what you're capable of doing. It's just we're not doing it in this class. The picture we drew of the general linear model looked something like this. So this was the OLS estimator. We just drew a line through the data the best we could. And we had two things we could control, both the vertical intercept and the slope. So how steep the thing is and then where it hits 0. Okay, so this is the basic idea. And I guess last class, we introduced this idea of the single sample t-test using a regression model which just includes beta 0. So we walked through this idea. We talked about the sample variation. So every time we draw a sample, there's some error. And this error leads to variability in our beta 0, our our intercept coefficient. And so that follows a t-distribution centered on so the central limit theorem tells us it's centered on 0, but we can think about it mathematically equivalently as being centered on the sample mean, and then we test for the p-values more extreme than 0. So this was our model, and it looks really simple, but this was a t-test. And the nice thing about code is we don't ever, again, have to perform t-tests using these like t-distribution tables you might find in the back of your stats textbook. It gives us just a ton of stuff. And so last class we talked about interpreting some of the regression outputs, and we're going to return to this today. And the way we would interpret this is that beta 0 is the estimated mean temperature. So we go through and we perform a fitting of this regression model. Beta 0 is the estimated mean temperature. And then we see a p-value, which tells us the probability that we see something as extreme as beta 0 given the null hypothesis. And this allows us to make claims about how likely we would expect the null hypothesis to be. So this is an incredibly powerful approach. We built a lot of our scientific apparatus on top of it. And then we moved on to testing relationships between variables. So we talked about this example last time, where we said on the vertical axis, our outcome variable is wait time. So how long do you have to wait? And then we built a model predicting wait time using minutes after open. So later in the day, maybe we have to wait longer. And the first place we start, as always, is to visualize relationships. So we start with a scatter plot, and then we think about the most appropriate model for the question at hand. And so in this case, we built a model with a slope. So our x variable was minutes after open. We had a vertical intercept, and then we had a slope coefficient. And in this case, the interpretation of beta 0 is slightly different. So you'll remember beta 0, and I want you to pay attention here. We're going to make a transition in a second, which will use these ideas. Beta 0 is the intercept parameter, which is the estimate of our wait time if we were to place an order exactly when the shop opens. So at x equals 0, what is our estimated model? So it's basically this point at x equals 0. And then beta 1 is how much y changes on the vertical axis every time we increase our x variable by 1. So we go from 0 minutes to 1 minute. Our y variable has changed by exactly beta 1. So we've increased our wait time by some amount as we increase the time we place an order by 1 minute, by 1 unit. In this case, that's 1 minute. Okay, and then so the p-values that we see in our model are essentially just the probabilities of seeing extreme events like 0 under the t-distribution given to us by the sample. Okay, so this is the foundation We are squarely in the lobby, sort of in the entryway. We've opened the door, walked in, closed the door, now we're inside. What we're about to do is build another type of regression model. We're simply going to take this idea and apply it to a different environment. And my bet is you're capable of building this model, potentially without having seen it before. But using the intuition we've been establishing, I think you can get this. So by the end of class today, I think we're going to have built a new model, which is exactly what I expect from this class, essentially the rest of the semester. From here on out in this semester, part 4 and the remainder of part 4 and part 5, we are essentially building models simply as extensions of the general linear model. They're all going to look something like this. We have a y variable, and then we have something on the other side. And we're going to be minimizing the sum of squared errors. Okay, so let's say I have this new question. Y'all on board with this? I just want to say, this is a powerful approach. This is like, whenever an economist sits down and tries to do something new with data, this is what they do. So I'm just walking you through what it is we do with data. So here's a new setting. I have 2 samples, or like one sample with 2 different categories. So on the vertical axis, I have temperature, which is a continuous numerical variable. So remember from part 1, we talked about different types of variables. This is just a continuous numerical variable. And then what I've done on the horizontal axis, we have a binary categorical variable. So we have either 0 or 1. If it's 0, it's representing low green space. So neighborhoods with fewer trees and grass and such. And then we also have neighborhoods with high green space. So Oakland tends to have a lot of trees. We live right next to a park. I mean, I don't live in Oakland, but Oakland is right next to a couple of parks, so lots of green space. So we'd probably be in this high green space category. But what's nice here is we can classify binary categorical variables as numbers. So we've just transformed a binary categorical variable into a binary numerical variable, just 0 and 1. And I wanted to show you the data set, because we're actually going to work with something similar to this in a second. But so you can download the data set, which is called dummy variable. So I have a temperature column, which is representing the temperatures in each one of these neighborhoods. And then I have a high green category. It's 0 if the neighborhood does not have a lot of green space. And then it's 1 if it does have a lot of green space. And we can play around with this in code. So this is just what it looks like, or what we call a dummy variable, which is a name I actually really despise. It's like not what I would name a variable type, but a dummy variable basically just represents 0 and 1. So it's like turning a categorical variable into a numerical variable. We'll define this a little bit better a little later. But they're incredibly powerful, so I don't know why they got called dummy. And even if they weren't incredibly powerful, it's sort of a disrespectful name. So yeah, we can see the temperature column, we can see the high green space column, and we could do a bunch of things with this, right? So high green is equal to 1, so we can just filter out all of the neighborhoods that have high green space, and you can see their temperatures here. So we could do a lot of things with this if we liked. If you'd like, I've included the notebook, so you can either construct your own as we go through, or you can just access the one I'm updating live. I don't think you get to see my changes as they go live unless you refresh the page, but you can see the notebook if you prefer working with it there. Okay, so that's what this looks like. So on the vertical axis, we have a continuous numerical variable, and on the horizontal axis, we have a binary categorical variable, or in this case, a dummy variable. And what this is doing for us is classifying our data into one of two categories. So if it has a 1, then it gets put at the 1 axis, 1 point on the x-axis. And if it's 0, it gets put at 0. So this is kind of a description of our data. Like we did in part 1 and 2, the first place to start with working with a data set is simply to try to understand it better. And one of the ways we summarize and work with data so that we can understand it better is simply through visualizations. So if I'm seeing this question, which is, do neighborhoods with more green space have lower temperatures? Then what I want to do is try to get a visual sense of whether that question is true or not. And the place I would do that is with a box plot like this. So I've jittered the horizontal axis for each of these categories, and then I just have a vertical axis here representing temperature. Okay, so this is the place to start. The second place to start, or the second step, I guess, is to think about what a model might do. So we have two variables, x and y, and I'm going to put this model up on the screen. And we're going to talk for a second about what this model might be doing. So, so our y variable in this case is temperature. We have a vertical intercept, and we have a beta 1 multiplied by high green, and then of course the error term. So this is where I want you to think critically about regression models. How would we interpret beta 0 here? Someone take a stab at this. Well, very aggressive terminology. Someone take an attempt. How would we interpret beta 0 with this regression model? I haven't done any work here. We haven't estimated anything. We haven't drawn any lines. But just what does a beta 0 get interpreted to mean when we have a slope? Yeah.
When x is equal to 0, temperature will be equal to beta 0 on average.
So on average, when x is equal to 0, y will be equal to beta 0. Yeah, very nice. So it's basically just the vertical intercept at x is equal to 0. So in this case, what's our x equals 0? Yeah.
Is it the low green space?
Low green space. So if we're saying beta 0 is equal to the average at x is equal to 0, then beta 0 is going to represent the average temperature for low green space. So when we build a model like this, we can interpret our beta 0 as this. Average temperature at x is equal to 0, which is the low green space locations. So beta 0 represents the average temperature in low green space locations. Okay, second question. How do we interpret beta 1? Just classically. Someone just give me a textbook definition here, beta 1. Corin.
Reaching increase in live radius with the increase in 1 in live radius with the increase to temperature of beta 1.
Okay, so Corin's saying, look, we increase our x variable by 1, which increases our y variable by beta 1, or changes it by 1. So how do we interpret, what's a 1 unit increase in this model? Is this a simple question? Corin?
It's just high grade or not high grade.
Yeah, so we only have 0 and 1, so increasing by 1, we just go from low green space to high green space. And then beta 1, as we go from low green space to high green space, changes on the vertical axis our temperature by beta 1. So beta 1 in this case is just the difference between the two categories. So 1 unit increase in x puts us in the high green space. So beta 1 is just interpreted as being the difference between these two categories. Okay, so this may seem simple and like a simple extension, and I hope it does. This is what the model looks like. We just basically draw a line from the vertical intercept at x is equal to 0, which represents the average temperature of the 0 category, and then we draw a line with a slope equal to beta 1 to the second category. So the average temperature in the first is just beta 0, and then the average temperature in the second is beta 0 plus beta 1, or more precisely, beta 0 plus 1 times beta 1, because we're increasing by 1 unit. And so that gives us a temperature that looks like this. And what I've done here is plot out some, actually just the estimates of each of these coefficients. So in this case, beta 0 is representing the mean temperature in low green spaces, which, as I've run the model, is roughly 22 degrees. And then the change in temperature as we go from 0 to 1 is negative. So beta 1 is the difference in temperature between these two categories. So question for you. How would we interpret these results together? I'm going to ask you to do all of these steps on your own in just a second. So be prepared for that. How do we interpret, or maybe a different question, could beta 1, this difference, being -3, could beta 1 be due to chance? Well, we kind of don't have enough information here. I mean, the answer is, like, in reality is yes. Like, any result like this, simply due to sampling, could be no different from, the truth could be no different from 0. We could get something this big simply due to sampling error. But to truly answer the question of, like, is the temperature actually lower in areas with more green space, we have to check the p-value. So what we're going to do, wow, who wrote these slides? Okay, that joke never gets old. So we're just going to test this using a regression model. So I've shown you some of the regression outputs, but let's just do this together in code. So I'm going to load the data set, and then I'm going to make a nice little plot here, which is just like what we saw in code, or in the slides. And then I'm including the prompts in the notebook. So this is what I asked of Gemini. What I'm wanting is a regression model where we have temperature is equal to beta 0 plus beta 1 times high green. And so what we do here is we just define the y variable to be temperature. We define the x variable to be high green. We add a constant to our x variable. And then we just put it into the OLS model, so the ordinary least squares, just minimizing the sum of squared errors. And this will build a model for us, and then we can look at the summary. If you like, you can not include the table suffix here. You can just print out the whole thing. But I think it looks cleaner. It's a little bit easier to read when we just see the coefficients and such. Okay, so we've done something like this last time, but I'm wondering if someone can interpret, or maybe I'll interpret the first line and then someone interpret the second line. So the constant here is just the beta 0. This is 21 degrees on average in areas with low green space. And this is definitely different from 0 because the p-value is essentially 0. We're rounding it down to 0. So what this tells us is that the probability of seeing an event as extreme as the one we do, a vertical intercept of 21 degrees, is incredibly unlikely. So it's very unlikely. This is sort of a meaningless intercept here. This is telling us that it's very unlikely that the average temperature in low green space areas is not 0 degrees Celsius. So not that meaningful of an output. Often we don't care so much about the vertical intercept. What we do care about in this case is this second line. Someone interpret this second line here. We've run a regression. We have an output. What is it telling us?
So the coefficient of negative 2.635 states that for every 1 unit increase in X, temperature is going to decrease by negative 2.635 on average.
Okay.
The standard error is just how far with the distribution, splitting the data 0.27 and then like 2 standard deviation or 2 standard errors, but
Okay.
the t-value of negative 9 states that on average this value is going to be negative 9.7 standard errors away from the mean.
Love it.
The p-value of 0.00 means that under the null there is, or we will see a value as extreme as negative 0.263 or negative 2.635 0% of the time. And then the 95% confidence interval shows that if we took many samples, 95% of the samples will have the true mean in between negative 3.174 and negative 2.197.
Okay, this is a very complete answer. There are 2 things I might change. Most of this was spot on, but I'm going to be a little bit more precise in a few things, if I can. So this is a really good description. We have this as our coefficient, so every 1 unit increase in our x variable, which means in this case, as we go from low green space to high green space, we see a decrease in temperature on average of 2.6 degrees Celsius. And then we have the standard error, which is just, exactly like we were talking about, like the variability in the t distribution. T is, and this might be where I would reword this slightly, is just the number of standard errors, our null hypothesis, and our sample mean are separated. The p-value, it was a great description here. This is, how likely is it under the null hypothesis that we'd see a slope as extreme as this? And then the 95% confidence interval just tells us we're 95%. If we run this model sampling with this size, 1,000 times, 95% of them will have the true mean, within that confidence interval. But it's not specifically these numbers. It's just the confidence interval that we would construct would contain the truth 95% of the time. Okay, yeah, so very nice. This was a very good description. These are the kinds of things that we expect from economists working with data. We have to not only be able to understand how to build a model, how to summarize data, but also how to interpret what the model is telling us. So in this case, I would conclude that the answer to the question is yes. To keep it as simple as possible, yes. And to be precise, it's a difference of, on average, 2.6 degrees Celsius. Okay. Okay, any questions here? To do what we did in class already today is an incredibly powerful skill set. If that's all you take from this class, props to you. That's a lot. But we're going to continue to build bigger models, more complicated models, and more flexible intuition for applying these kinds of models in new situations. So we're going to run through a bunch of steps. You're actually going to run this on your computer if you have it. And if you don't have a computer with you today, you can just hop on someone else's. So the first step, so we have this example here. We have neighborhood income and pollution. We want to answer the following question, which is, do low-income neighborhoods face higher pollution levels? We're going to be working with simulated data. So this is not, the estimates that we run today are not going to be something you should, write up in a, in the school newspaper. Like this is not, these aren't real results. But the results we're working with are consistent with what we've done in the field using real world data. So the place we start here is by summarizing the data. You can find the data set by clicking on pollution. So you can download the data set here, and that pulls up a data set. So we have two columns. One, we have pollution, and then second, we have a binary indicator variable for two categories, whether the neighborhood is high income or low income, based on the average income in the neighborhood. And then what we're going to do is try to summarize the results here. And we can do this with a visual. So we're going to do this on our computers individually, but I do want to talk through this step by step. So no one's going to get lost. We're going to do this step by step. And you can always reference my code in the notebook. But I would like you to tell me regression results before we actually put them on screen. Okay, so we have a continuous numerical outcome variable, and then a binary categorical variable, or binary indicator variable in low income. So if someone suggests something, how would we visualize this data to try to answer our question? Yeah.
You did the same thing, we've split it between low income is one on the x-axis, and then high, whatever isn't low income on the other, and then jitter, like the amounts of pollution.
Okay. Yeah, so very similar to what we just did. We have, on the horizontal axis, we have 0 and 1 representing our two categories, and then on the vertical axis, we can just, because that's a continuous numerical variable, we can just plot it, and then maybe add a jitter, just so we can see the data better. Yeah, very nice. So maybe something like this. Okay. So great. And we can do this in code too. I put it in the slides, but I just asked, so plot temperature on the vertical and 2 box plots, one at 0 and one at 1, according to low income. And let's see what we get here. Ah, yeah, there we go. Nice. So we have 2 box plots. This is good enough. We could also add a scatter plot. Looks like this. And then if we wanted to put the scatter plot on top, we could just do Z order, make this go behind. Okay, so we've summarized our data. I think the one I made is a little prettier, but you can always play around with these things until you like what you see. So if you were just looking at this, we have our question at hand, which is, it's a really socially important question. Pollution is not a good thing, and we might be concerned that low-income neighborhoods have higher levels of pollution. And so we've gone through and visualized our data here. Just looking at this picture, I would expect that, yes, if you're in a low-income neighborhood, it certainly looks like your pollution levels are higher, which is a concerning result. But we also can't just stop here, right? We need to check whether this is statistically different from noise. Like, is this consistent with our null hypothesis of no difference in pollution levels between the two groups? So the next step is to build a model. So someone propose a model here. Actually, let's pause. I want you to write a model down in your notes and then check it with someone next to you. We'll take about a minute here. So like this will be a considerable amount of time. I want you to write a model down that might do what we want, and then check it with someone next to you. Go. Someone want to propose a model? What are we going to do? How do we build a model that would do something useful for us? Can I get a temperature check? How many of you are totally lost? One finger. 2 is like medium lost, like doing okay but struggling a little bit, which is a great place to be. And then 3, it's like, I know exactly what I'm doing. Temperature check? Okay. I love 2s. I love other numbers too, but so you know what we're doing, right? Someone propose a model. Yeah, Ben.
Could we just use the one from the previous that instead of hybrid, we just use the
Okay. Yeah, so something very similar to what we just did. So we have pollution as our outcome variable, which is what Ben's proposing. We have our vertical intercept. We have beta 1 times our low income dummy variable. Anyone do this differently? There are a couple of ways of doing this. Unfortunately, there isn't just one way, but this is a pretty good approach. All right, so it's your job next. I know you can see my code, but I'd like you to translate this regression model into code and then run it. So we're going to take maybe 2 minutes here to set up a regression model to do this. Feeling comfortable here? And someone next to you will be good for debugging if you run into issues. But you can ask Gemini something along these lines. I want to regress pollution on this model. And then that will translate the statistics into ECON. And then I'm going to look for some numbers in a second. Okay, someone tell me, what's the average temperature in the non-low income group, the high income group? What's the average temperature here? Okay, and what are we doing to get that number? Like, what are we interpreting? The y value when x. Yeah, nice. So our beta 0. Okay. And what's the average slope between high income and low income? Like, on average, how different are these two groups? Yeah, Luke.
15.89.
So
it's just like the difference between like the medians of the two box plots.
Okay, so you took the medians of the two box plots and took their difference. Okay.
We're kind of like the averages.
The
Of the
and was this retrieved?
categories.
Yeah, nice. So it's, we find the average in both, and then we take the difference. And do we know if this number is statistically different from 0? Are we confident that getting a slope is not a result of random error? Luke.
The p-value is like extremely small, so
Okay.
we should be fairly confident.
Yeah, this is about as confident as we're ever going to be in science. These are very extreme p-values. In your next homework, you're going to see some results that are not this extreme. But what Luke is saying is we get a difference of 15 between the averages. And that difference, like the slope parameter following a t-distribution, is very unlikely to be the result of random chance under the null hypothesis. We're very unlikely to see this result given the null hypothesis of zero slope. Okay. So if you were seeing all of this together, someone who hasn't answered anything today, how would you interpret our results? Like in one sentence or maybe two sentences. Someone who hasn't answered me today. How would you describe these findings in English? And to someone who may not understand the model. This is a great exam question. And now's your chance to be wrong. Actually, instead of one answer, I'm looking for three. Looking for three different answers. Three different variations on the same result. I think I can wait you out. Someone help Luke out. Luke is volunteering, but he's answered so much already today. Yeah.
The positive beta indicates that neighborhoods have different levels of pollution, one higher than the other.
Okay, so nice. So we've said a lot of what's going on here. We know that they're different. And we know, there's a slope here. Someone add to what we just said. We're stating that the two neighborhood types have different levels of pollution. What else can we add to that sort of summary? There are a couple of other things. Yeah, Garrett.
Even without regards to the income of the neighborhood, there'll still be like a pollution level of 15.
Okay, so like thinking about the beta zero, so there's like a baseline level of pollution in non-low income neighborhoods. What else can we add? There's still a couple other pieces.
Like going back to the positive or slope, we can conclude like on average based on the data that low income neighborhoods will have on average have higher air pollution.
Okay, so on average, low income neighborhoods have higher pollution. So we can say that they're different, but we can also be more precise by saying that low income neighborhoods have higher pollution on average. We can say some other things in addition to that. When we make claims about our statistical results, we should also include some statement about how confident we are about the results. So how would we include the p-value in a communication of, or a communication in English? We could say this is very unlikely to be due to chance. So that would be, I would say, like most of what how we would make claims about our results. Like we can, the important pieces here are, we're talking about the slope, we're being specific about what the slope is telling us, which is that low-income neighborhoods, on average, see 15 units of pollution higher. And we're very confident that this is not due to chance. Luke?
Question, so like, so we have extremely low p-values, so that basically means like, there's a very, very extremely low chance that like we will ever see like values that deviate as far, or like we'll see like values as extreme as the ones we observe.
Yes, under the null hypothesis. So if there isn't a relationship here, if pollution levels are the same in both neighborhood types, then it's very unlikely that we would see something this extreme under the null hypothesis that they're equal. So if in reality it was true that pollution levels were the same, we would almost never see a result like this, which is the interpretation of the p-value. Okay, so this is a complete process. These 4 steps to go from not knowing something to being able to answer a question. We take our data, we try to summarize it in a way that's informative to our question. We then build a statistical model to try to test whether our question can be answered. And then we fit the model, and then we interpret the model. These are 4 steps. This is what I'm looking for on a final project. Okay, any questions here? So before we continue, next class we're going to start talking about extensions of the simple linear regression model. So we're going to start introducing the possibility of more than 2 coefficients, so more than just beta 0 and beta 1. But we have to spend a little bit of time thinking about where we can run into problems with our statistical models. There are a couple assumptions about OLS, or these regression models. We're just going to talk through some of these. I'm going to show you some pictures, and then we're going to pick this up next time. So the first is linearity. So we have to assume that there's a linear relationship between x and y. So if you remember back to part 2, when we talked about data transformations, we performed like log transformations of scaling data. We can transform x or y variables into something that could become linear. But the assumption of the model itself is that the variables are linearly related. So if we see data that does not look linear, then linear regression is not the right tool. We have to do something else. We will talk about how we can fix this problem, turning nonlinear data into linear data, which we can then apply the linear regression to. But we have to be careful here. And then independence. So this is essentially, we just need the observations to not be related to each other. So if you see time series data, often one data point will be related to the data point in the time period before. So you often see like these sort of trends in the data. This is not independent data. There are ways of dealing with independent data where we can turn it into something that is independent. But we have to be careful here too. So we'll talk about time series. This is a fancy term for something that I'm going to show you through a picture is relatively straightforward. Homoscedasticity is essentially the assumption that we need the variability around the model to be the same for all x values. So we can't have variability be different at different points in the data. And then normality, so we need the error term to be normally distributed. This one is, I should put an asterisk here. If our sample size is large enough, we actually don't need this. And the intuition is very similar to the central limit theorem intuition. If our sample size is large enough, we actually don't need the distribution of the data to follow a normal distribution, right? Because the central limit theorem allows us to make claims about the distribution of this sample. So this one's a little bit fuzzy. This is a technicality, and so we talk about it.
How do you know when your sample size is large enough?
Yeah, great question. We don't. Yeah, we generally think of like 30 to be roughly around the point where it, it's very difficult to be kind of wrong beyond that. But if we have a lot of regression parameters, we need more data to be confident. If any one of these assumptions isn't met, then our model can be wrong. Like our p-values will not tell us correctly the probability of seeing the event as extreme as the one we do under the null. So next time I'm going to show you a bunch of pictures. They look like this. And then we're just going to talk through each one of these things and extend to multivariate. Congrats, go celebrate your mini exam. Go get some sunlight. I will see you all on Thursday. Homework is due tomorrow if you haven't done it.
I think I accidentally wrote the wrong